So I'm going to claim today that the worst kinds of lineups are the stateless ones that treat you unfairly. Last month, I was hanging around at home and I ordered some sushi, and apparently got delivered to the wrong address. It never arrived. Turns out you need to call for a refund. So I call, I get transferred. I'm on hold for an hour, and then the line disconnects because apparently I've been on hold for too long, and I lose my spot completely. Just as bad as when someone cuts in front of you in line. Computers don't need to treat us so unfairly, so let's make the case today for when they shouldn't. My name's Logan. I work on scaling checkout at Shopify, which often means keeping the lights on for some very large flash sales. I'm going to be advocating for stateful throttles today. But first, a brief word on Shopify. Shopify is an all-in-one commerce platform that enables millions of merchants worldwide to quickly set up an online store to sell across multiple channels, online and offline. So I'm going to focus on a scalable stateful throttle that we shipped on our application layer, moving away from a previous legacy rate limiter that lived on our ingress. Was a bit unconventional, but we've been very happy with the benefits thus far. So in code, just as a small demo example, we're going to be building toward a stateful queuing library that schedules users to poll for their turn and lets them through when they're both eligible and the system has capacity. So here's a plan, a bit of prior work on this topic, a bit of background, and then we'll get into some of our own ideas. First, let's talk about Flash. Flash sales are what Shopify calls limited product availability events that drive huge thundering herds of traffic in a short period of time. You can think of those wild yearly Black Friday blowouts, but now happening daily and simultaneously for many merchants across our platform at any given time. And so I'm going to speak about these traffic bursts from a commerce-centric perspective, but it's easy to imagine these becoming more and more common for any application that can generate hype quickly. And as it happens, Shopify hosts quite a few drivers of this sort of hype traffic, from Kylie Cosmetics and Gymshark to Union LA and Kith. Often these brands can drive very high demand in very short time periods, competing for a limited supply of products. Just quickly, here's some numbers from our last Black Friday, Cyber Monday, which is usually our biggest event of the year. Many merchants will run flash sales simultaneously at that time. And our peaks will be processing, millions of dollars a minute. And to give you an idea of that sort of processing, it'll include terabytes of MySQL reads per second, as well as billions of background jobs and third-party API calls. It's also not uncommon that 1 year's BFCM will eventually become another year's baseline traffic. So, digging a little deeper, here's a quick look at Shopify's tech stack. We'll walk through this from a traffic standpoint in a moment. But generally, you'll see we're using a monolithic Rails application with a few different data stores, primarily MySQL, Memcached, and Redis. You'll also see we're serving traffic from GraphQL and REST APIs. So I'll walk through our traffic using green and red arrows to denote reads and writes. Our first traffic surface is browsing storefront, which is read-heavy, as you'd expect, loading data like product pages and merchant branding from a mix of Memcached and MySQL. Adding a product to cart will persist it in Redis. During checkout, MySQL writes and third-party API calls can happen, for example, around taxes, addresses, or shipping rates. And then submitting payment persists a record in MySQL, and on queues a background job for processing. Redis is also used at this step to reserve inventory. And then lastly, confirming each order also on queues a number of asynchronous writes to finalize things like inventory allocations and fraud analysis. So checkout overall is very write-heavy and can involve third-party API calls. Its traffic profile is not very cacheable, and the data that is cacheable can often be bottlenecked on a small set of keys. So that's a problem for us, since flash sales can drive huge bursts of checkout events in the span of a single second. Often these big events can happen so suddenly that it's difficult for cloud scaling to react on the fly. We could over-provision our resources, but they'd often be sitting idle and it would be difficult to justify the costs. Half a decade ago, it was a lot more common for things like this to cause outages. And social media has always been an outlet to find out quickly when buyers are vocally displeased. In Shopify's case, this bears a reputational risk to our merchants and is something we can't tolerate. So to prevent these outages, we need some sort of back pressure on upstream traffic to vent off overheating and give the system time to cool down. In checkout, buyers will experience that back-off pressure as being entered into a queue to wait in line. We'll assume that the user got placed in the queue when they tried to check out, and they're now polling the system to ask for their turn. WebSockets could also work here. There's a lot of different ways we can design and implement that queuing system. For years, Shopify handled checkout users by a simple stateless rate limiter that lived on Nginx. And then eventually, this moved to our application layer when we found a way to feel comfortable introducing data stores to our solution. So we're going to work toward this stateful approach in Redis, but we'll start by building up some context on rate limiters. So first off, the most obvious thing we could do is simply queue users directly in first in, first out order. In spirit, that would be ideal. It does impose a stateful memory requirement, but there's something to learn from the inherent fairness of tracking buyers in the order that they arrived. The main problem is similar to what happens when you're waiting in line to pay for something, and the person ahead of you is taking forever fumbling with their change. A FIFO queue blocks traffic one person at a time, so we can't make any progress at all while we're waiting for them, even if we could have served 2 or 3 users in the meantime. So for systems like this, you may have seen Little's Law relating average queuing to average throughput and response time. We can also think of this in terms of average checkout payments throughput being made up of average number of buyers checking out over how long buyers are spending in checkout on average. So from Little's Law, it's easy to see then how slow buyers slow down flash sales and cause long lineups to build up behind them. We're going to want to look for approaches that aren't just waiting for each single buyer to finish paying. So one of the simplest things we could try is called a leaky bucket. So just like a funnel, requests flow in quickly at the top and then drain out smoothly at the bottom at some constant drain rate. If we choose to care about order, then we call that leaky bucket as queue, which is stateful, and it's no different from the FIFO queue we showed earlier. And if we don't choose to track order, then we call this leaky bucket as meter, which is stateless and only needs to monitor capacity to decide whether to forward or drop requests. And actually, when we don't care about order, leaky bucket as meter is the same as a token bucket, which you've probably seen before. Is it there? There we go. So where leaky buckets drain at a constant rate, token buckets refill tickets at a constant rate. You could think of this like marbles in a jar. Requests come in and ask for marbles. If there's enough marbles available, requests are let through. Otherwise, they're denied. And so our marble refills are really just a mirror image of the leaky bucket's drain rate. At any given time, the maximum burst of requests would be the bucket size beta if the jar had been full of marbles. And so that's about as simple as stateless throttles get. You can actually combine token buckets with leaky queue buckets to support burstiness with traffic smoothing, but there's still some limitations. We've got a couple things to consider. Bucket approaches do well at policing capacity, but are not particularly great at preventing slow buyers from starving out the continuous flow of payments. Another issue is that because buyers that don't get in right away will eventually need to ask again for their turn, there's this opportunity for them to race with each other when they're polling the system to ask for capacity. And so that retry issue introduces this sort of unfairness where someone that arrived later might happen to retry at a lucky time, so they get in before someone else that arrived earlier. So we're going to want to keep these three properties in mind for the rest of the talk: capacity, starvation, and fairness. We're going to try to think about ways to improve on some of these properties. Windowed approaches are one thing we could do that usually starts to add a bit more state to the system. The simplest here is a fixed window where we count requests, for example, 1 minute at a time. So each request increments a counter in the window. We block requests when the window exceeds its capacity. And then the counter resets in each new window. So this is sort of similar to a token bucket that refills a full jar of marbles exactly once per window, but the implementation is even more straightforward. In code, it's as simple as storing a single counter tied to the window and then expiring it at regular intervals. And because this is so simple, it can work very well on keys inside some in-memory data store like Redis. And Redis happens to be very good at guaranteeing speed and atomicity for handling transactions on simple keys like this. We could also use a Redis Lua script to do the same thing. And storing Lua routines in Redis and then calling them atomically from application code is a powerful technique that we use often at Shopify. This will show up again in a bit when we talk about using a similar technique to drive different parts of the checkout queue. So the problem with fixed windows is what happens when requests come in right around window boundaries. So even though each individual window is doing its job at keeping less than our target service rate of 2 requests per minute, if we focus in just before and just after windows, we can see that it's actually possible to allow more than our target traffic to pass. Actually, up to 2x our target rate can happen across windows. And we're going to want to try to avoid that. One thing we could do instead is use a sliding window that counts waits in the previous window, depending on how far we are into our current window. So in this example, we're 1/4 into our current window when a request arrives. So we consider 3/4 or 75% of the previous counter plus the full weight of our current window. In this case, since 1.5 from our last window plus the current window's rate is still less than our service rate of 2 requests per minute, we accept the request. Then as we slide our window along, the weight for our previous window decreases, but we're rerunning the same calculation. So then this time 1.04 from our last window plus the current window's weight is greater than our service rate of 2 requests per minute, so we deny the request. And then eventually the wait for the previous window is low enough that requests will start to get through again. Then, of course, there's some variation on the approaches shown so far. Sliding window log is similar to what we just showed, but instead of using waits, it tracks the timestamps in memory and then pops outdated entries as our window moves along. Generic cell rate is similar to a metered leaky bucket, but it's using predicted arrival times in the future to check capacity. And then, of course, there's also approaches using adaptive concurrency and congestion control algorithms. So, semaphores and TCP-style congestion window approaches. So you can imagine something like TCP's congestion window would fit in this space because we could have algorithms adaptively adjusting our window size depending on different loss and throughput signals. At that point, we start to get pretty good at limiting request starvation. So overall, windowed approaches have done very well at policing capacity, so controlling the number of concurrent buyers in checkout, and avoiding starvation, so keeping the continuous flow of payments throughput during the sale. But nothing we've shown so far has actually done anything to improve fairness during that retry phase where users poll for their turn and compete with each other to ask the system for capacity. So we're going to aim to move beyond just throttling, and that's going to be the main focus for the remainder of the talk. We're going to walk through several steps building towards a more stateful and fair checkout queue. We'll discuss our initial stateless approach that lived on our load balancers. Then we're going to introduce the stateful second version that lives on our Rails monolith application tier. And finally, we'll talk about our rollout strategy in moving from one to the other. First, we're going to focus on our stateless edge tier legacy throttle. Per this diagram I shared earlier, the legacy throttle lived on our Nginx load balancers and would regulate whether a shop's throttling had engaged and inbound checkout requests needed to redirect to the checkout queue. In order to do so, Shopify leveraged an incredible tool that lets you extend Nginx called OpenResty. OpenResty enables Nginx load balancers to be scripted with Lua and is used extensively at Shopify. It's a powerful tool to manipulate request and response traffic on the fly at various stages. It's stable, fast, and very scalable. We've used it for multi-data center routing, DOS mitigations, cache control, profiling our applications, and numerous other use cases. Just to give a quick example of this, this is configuring Nginx to listen on a port, serve some simple content, and it's using OpenResty to inject response timing information in a header. And as I said, one of the cases we've used this for is our legacy checkout throttle. So the way this used to work, when Nginx detected that a checkout should be throttled, it would fetch and cache branded throttle assets for that shop from our Rails monolith. The throttle assets included JavaScript client logic to poll in the background until capacity was available. And users would keep polling on the throttle page until eventually, when there was capacity, Nginx would redirect to checkout and to the web form for the user to collect payment. Unfortunately, there's a problem with the way this is implemented, which is that we still have this unordered polling phase that I mentioned before. So let's say a flash sale lasted for 20 minutes, and I arrived in the first few minutes of the sale. I've been waiting for 15 minutes, but there's still plenty of people ahead of me that also arrived very early. And then someone arrives at the 15th minute, and they also get into the checkout queue. But it just so happens that this person that arrived at the 15th minute pulls at a lucky time when the load balancer happens to have capacity, and they get in ahead of me, and ahead of the 15 minutes of buyers who arrived before them. You can imagine sitting in the same room as a friend when this happens. They barely tried and just copped one of the last pairs of some hype sneakers you waited 20 minutes for. You're not going to be very happy on Twitter. So we've got to do something. We can start by assigning an encrypted signed ticket to each user, marking the timestamp when they arrived. And then we're going to aim to prioritize early user tickets over very recent ones. So let's say this is our timeline of tickets that we've issued so far. And we want to try to prioritize our oldest tickets during the flash sale. At any point in time, the problem that comes up is where do we draw the line on how recently issued we should accept tickets. Of course, the more tickets we accept, we'll have more eligible users competing for product, and so inventory is more likely to sell out quickly, which is something we want. On the other hand, with more users competing, it's more likely that a late arriving ticket will get in ahead of someone who came in much earlier. So with this approach, we need a way to decide the most recent tickets we're willing to accept at a point in time. And at the time, we drew inspiration from control theory algorithms regulating thermostat temperatures. So as flash sale traffic got hotter, we could try to cool down by accepting fewer tickets and being stricter about prioritizing our earliest users. And if flash sale traffic was cooling down, we could turn up the heat on how many tickets we would accept to ramp up throughput. Walking through that more slowly with accepted traffic in green and rejected traffic in red, we have this lag slider to decide the most recent tickets we're willing to accept. If we see traffic ramping up and we want things to cool down, we reduce our slider to be stricter about prioritizing our earliest tickets. And vice versa, if we want things to start heating up again, we can move our slider to the right to accept more recent tickets at the risk of an older user losing out. And so this approach was pretty flexible without using much server-side state. And in practice, we found it was pretty good at ensuring very lagged users rarely got in ahead of very recent ones. So the users that came in at the rightmost, very rarely would they lose out to the users that came in at the leftmost. But because the system was trying so hard to be stateless and work without any ordered data structures, we found that the window didn't stabilize well, would fluctuate often, and fairness was actually not very consistent. Because it lived on our load balancers, it also made it a lot harder to test and maintain that new features wouldn't break flows engaging the checkout queue. And also, because it lived on our load balancers, this made it difficult to scale to regional clusters, adding new load balancers, since not all load balancers, they weren't sharing state, so they didn't all have the same view of where the lag slider should be at a point in time. And lastly, another major problem with this approach was that Nginx had no awareness of the inventory in a user's cart. So it was totally possible that a buyer could enter the checkout queue, wait for 30 minutes, finally get through to their turn, and then they find out that actually the inventory they had in their cart had already gone out of stock 20 minutes prior. And that's just a shitty experience for everyone involved. So what we want to move towards now is our stateful second version of the checkout queue. This is the one that's going to live on our application layer, and it's going to surface personalized information, such as the state of inventory in a user's cart. And it's also going to work very hard to order users as fairly as possible. And with fairness in mind, one idea that will stay the same from our previous throttle is this idea of issuing encrypted tickets to the user, marking when they arrived. So if we think about our traffic profile again, we'll see that most of our tickets arrive in a big spike near the beginning. So in statistical terms, you could say our arrival times seem to follow a long tail distribution. And we'll flip this around just to match another visualization in a moment, but it's really just the same thing, just right to left instead of left to right, with earliest tickets now on the right. And then a brief note that modeling this sort of traffic is actually not super trivial for statisticians, but for our purposes, we're going to pretend our tickets are distributed into normalized buckets. I've actually brought this to demonstrate, so this is called the Galton board. If anyone wants to mess around with this after, just let me know. So basically, even with a lot of users, most of our users arriving very early on, some users will still be either much earlier or later than others. And so the arrival ticket times are going to land in different buckets with extremes at the ends, and most tickets arriving at specific times in the sale. And what's interesting is that there's actually some implicit orderings that arise on those buckets. One of the orderings is among the buckets themselves. So there's this natural queuing between very few user tickets arriving in the extreme earliest bins, and then most user tickets, which were also early on, and then a tapering off of users that arrived much later in the sale. But that's not our only ordering. And if we suppose each bin represents a particular second in the sale, then there's also this ordering within the 1 second bins themselves. So if we say from left to right that the first bin is the first second into the flash sale, then the next bin is the next second into the flash sale, and third bin is third second, and so on, then within any single second, there's also this ordering of users between those that arrived in the first 10 milliseconds of the second, those that arrived 100 milliseconds later, 150 milliseconds into the second, and so on. And so by grouping and ordering our users into buckets like this, we can strive to limit unfairness between the queue bins, but tolerate unfairness within the bins themselves. So, for example, we might work to ensure that no user, as long as they're polling, can be cheated more than 2 bins apart, but losing out to someone within their own bin is tolerable. So the design of our system is built around this. It's built in 2 parts. We're using both a rate limiter, similar to the ones we discussed earlier, and also a scheduler with awareness of when our user tickets were issued. And we're going to build up this library as a Ruby gem, which will eventually live inside of our Rails monolith application. And both of those key parts of the system are going to be driven by Lua scripts, which we store and execute atomically in Redis. So a rate limiter is going to be responsible for tracking which shops need to be throttled, redirecting a user to the checkout queue if a particular shop needed to be throttled. And then when a user is eligible to proceed, the rate limiter is going to have final say on approving whether the system still has capacity to let them through. And our scheduler is going to be responsible for regulating the ordering among queued users. It's going to advise users when it's their turn to poll for capacity. It's going to handle those poll requests when they come in. And it's also going to have awareness about whether users are polling too early or too late, so that we have flexibility to penalize them or adjust accordingly. And the interface of our queuing library is going to look like this. We can wrap blocks of code to check whether a queue is engaged and then act differently depending on whether the user has a ticket to proceed or not. And then for users that are redirected to wait for their turn, our gem is also going to inject a GraphQL handler to serve their pull requests. And in Ruby, in Rails, typically this handler would live in a middleware that's going to run very early in the request lifecycle, so before any other external I/O. And as we showed earlier, and we'll come back to this in a moment, this is a simple prototype application using our library. So we redirect to the queuing page if the gem says our throttle engaged. Users pull our GraphQL handler for their turn, and then eventually they're going to receive a ticket to pass the throttle. So we'll also talk about the scheduling algorithm underlying this. There's basically 3 key pieces of state that we're tracking in our scheduler. Latest bin is the bucket assigned to the most recently issued tickets. Client bin is the bucket number assigned on a particular user's signed and encrypted queue ticket. And lastly, we have a working bin, which is essentially the maximum bucket from which users asking for their turn are eligible to proceed. And there's some flexibility around how we increment working buckets, which is one of the most powerful parts of our algorithm, as it can adapt to whichever signals we choose. So first, just looking at this in Lua, essentially we have one throttle key per shop, which is representing a dictionary of fixed fields. So that's the only key our script needs to know about, which makes it easy for us to consistently hash across different Redis instances. In this snippet, we're rejecting a client that pulled with a client bin that was too high, and then using a single Redis command to persist signals, such as whether the clients are pulling on time, to allow us to determine when to increment our working bin. And then the script itself is optimized to use very few Redis commands because it's operating on just this one key. And in Ruby code, we have a snippet to decide when to ask clients to poll again, which is very simple, as it's basically just how far away was the client's bin from our current working bin, multiplied by how long we currently expect to spend on each bin, plus some jitter so that pull requests from the same bin aren't all synchronized to arrive at the same time. And then lastly is our inventory awareness that we get for free from our application layer. Our throttle lives right alongside Shopify business logic in the monolith application. So inventory state like this is readily available and super easy to cache without any round trips. Our web client itself is also a stateful React application, so it's easy to enrich with additional merchant branding and customization. So apart from the benefits to fairness and user experience that we're getting from statefulness, it's also proven to be an enabler for scale. So some benefits are surprisingly counterintuitive to our initial fears that Redis could become a single point of failure. For starters, the state we have is very easy to cache at multiple layers. We can cache the working bin since we only need to update it so often. We can cache the user's inventory. Most of the time, our requests don't even need to hit Redis. And our working bin itself is also super adaptable to different feedback signals. One of those is compliance. Our users polling at the times we ask them to, not too early or too late. The working bin can adjust accordingly. Also, is the system healthy? Does it have capacity to allow more traffic? That's another signal we can use to adapt. And surfacing inventory itself is also a back-off signal, since instead of users polling endlessly for 30 minutes, if we surface to them that inventory has gone out of stock, the traffic will naturally back off. And then lastly, the bins themselves, by virtue of being partitioned, lend themselves very easily to sharding across multiple Redis instances. So finally, we'll talk briefly about our rollout strategy, migrating this to production. And as you can imagine, this is a critical piece of our infrastructure, so it's protecting our platform, and so it's very important to roll it out safely. The way we went about this was a lot of fun and really just rooted in running a lot of experiments. We wrote simulators and prototypes at every phase of development. So for starters, we needed to test if our production monolith could actually handle our target poll traffic. So we added a profiling middleware to our production monolith, which would short circuit very early into the request lifecycle on a specific benchmark URI. And this is basically prototyping what our poll handlers would look like. So the middleware is pretty much just benchmarking various Redis externals to measure if our planned approach would be feasible. And we were very impressed to see that it was responding within milliseconds and easily sustaining the millions of requests per minute that we needed. So next, we want to actually test and compare the different algorithms in Redis. So if you've seen, for example, simulations of how amusement park queues react to different visitor behaviors, that's going to be a similar concept here, where we can specify in configuration different types of client behavior. So for example, not everybody needs to be polling exactly when they're asked. We might have some bots trying to be sneaky and poll early. Or maybe some users close their browser and disappear completely, or network latency issues. And then, of course, we can also add some random network latency as well to make this a bit more realistic. So we'll take our input configuration of users, and then this is written in Go, so we're spinning up Go coroutines to simulate their behavior concurrently in checkout. And at the end, we can aggregate our results to compare different algorithms. This is a quick demo. It's open source. You can check it out if you like. But so basically, it's simulating clients arriving over several consecutive windows of queuing. And it's continuously streaming real-time metrics to a dashboard for review. So our dashboard has a bunch of different metrics. See, we have utilization to measure how many checkouts are happening per minute. We also have metrics to compare how fair different algorithms were, so which types of clients were most impacted when unfairness did occur, but also how many seconds could clients be cheated by different algorithms in the worst case scenario. And eventually, we had enough data to feel pretty confident in choosing a scheduling algorithm. So then the next step was to actually roll it out in our portable queuing gem and benchmark it in production. So we were able to load test this both as a very simple Ruby app, but also a mock API that we exposed directly in our monolith. Our internal load generator is called Genghis. It's written in Go and makes it very easy to spin up concurrent worker VMs, which are each acting as clients for our services. So we can actually script different checkout behavior, similar to the simulator I shared earlier, but benchmarking our deployed applications at scale. So, for example, we could simulate millions of users per minute trying to check out on this mock application I showed earlier. Or we could also generate considerable load on our actual Rails monolith application via this mock API, which is benchmarking the queue at high fidelity to production. And looking at our results, it performed better than we expected. P99 response times were just a few milliseconds. We could serve millions of pull requests per minute, and thousands of users completed their turn, exiting the checkout queue each second. So overall, we were very happy with the results. And looking back, we learned a lot through rolling out our stateful checkout queue. As we said early on, most standard rate limiters didn't really work for us because of this race to poll drawback. where users have to retry to ask for their turn and are competing for capacity at that step. We also showed some benefits of queue state to fairness and user experience. So fairness being our actual ordering of users into buckets, and user experience being inventory surfacing and personalization. Our stateful approach also turned out to be very scalable and resilient, both horizontally from the way our bins make it very easy to partition across different Redis instances, but also adaptively in the way that our working bin can be modified to different signals, such as system health and user behavior. And then, of course, all the simulations we ran during our rollout also proved to be an effective strategy in building confidence to migrate such a critical piece of our infrastructure. So I hope that some of these considerations can be useful for others weighing approaches to user-facing queues. I'm happy to chat further, but I am low on coffee and really need one soon. So feel free to grab me over lunch or on Slack or reach out online. Thanks.